Hello everyone, welcome back. In today's video we're starting unit 10, so this is curves defined by parametric equations. So this begins our last unit for single variable, and this is parametric and polar curves. So parametric and polar curves begins a 3-unit bridge, I would like to say, and this bridge connects multivariable calculus with single variable calculus. Now, even on its own, just in single variable calculus, parametric curves and polar equations are very important, and it is important to analyze how it works with calculus. But essentially what happens is this is an intro unit that gets us prepared for some of the more complex topics, along with 2 other units at the beginning of multivariable calculus, which will be 3-dimensional space and vector valued functions. Once you have all those 3 units done, you're prepared to do calculus in all dimensions. However, we're only starting with some single variable calculus, and we just got to be proud that we're even finishing this. This is a great accomplishment. Anyways, we are going to get started by discussing some parametric curves. So I don't know if you've done this in pre-calculus. I'll assume that you have a slight background with it. We're not going to spend too much time discussing the algebra, only this video really, and it's not going to be very comprehensive. But we really want to put emphasis on the calculus of these curves. But essentially, the way that we define a parametric equation is we have 2 equations, or more than 2 equations, depending on how many dimensions we want. For 2 dimensions, we'll have 2 equations. This will define an ordered set based on equations of a parameter. So in 2 dimensions, this will be an ordered pair. So we'll have P of x, y. And this point will be modeled by some curve, C, and that will be x of t and y of t. So basically what happens is you have an equation x of t equals f of t, or something, a function of some sort, and this models the variation in the x-coordinate of this point. We also have y of t, that's equal to some other function of t, g of t, and that models the y variation. So we have models for the y variation and the models for the x variation, and then when these functions play out over this time parameter, then we get some curve. And what's nice about this curve is it's not constricted to being a function. It can be whatever we want it to be, but the important thing is it moves in some direction. So we'd have a starting point, and then we'd have an end point. And this moves through time, or this moves through the parameter of t. So t might go something like this, and it will trace out this curve at a certain velocity. And then we could also have periodic motion. So we could go around multiple times, depending on how many times t goes around. Or this curve could also just be like a parabola, and it could only go around once, and t would go that way maybe. That's basically what a parametric curve is. Let's just do a couple of examples to get everybody sorted out before we start moving on to some calc. So here's an example. I would like us to sketch the following set defined by the parametric curves. X of t equals t squared minus 2t, and y of t equals t plus 1. Okay, now I would say the most efficient way to do this is essentially to use brute force to do this. So you make a big table, make a t table, you make an x table, you make a y table, you've got a big column, you've got another big column, and you just plot out different t values. So why don't we start with like -2, so -2, plug in -2 for x of t and y of t, and we are going to get 8, -1. We try at 0. Let's try for 0. For this we get 0, and and then 1. Let's try for 2. Then for t equals 2, we get 0 and 3. If we plug into the equation, and then finally let's try 4. Do 4, we get 8 and 5. Okay, so now we've got all these points. So now if you take the x column and the y column, you've got each point corresponding to each time interval. Okay, so now we can actually graph this. So we've got a graph here. And now what we can do is we can just plot some of these points and see what our curve looks like. So if we do that, we are going to see that at t equals -2, Be all the way out here at y equals 8, or y equals -1 and x equals 8. Then we're going to go to t equals 0. T equals 0 is at 0, 1, so we're going to be about there. Then we go to 0, 3. Then we go to 8, 5. Looks something like that. So it looks somewhat symmetric. And what I would like to do now, to look at this symmetry, is we're going to choose the point, how about we choose the point 1 to look at. We're choosing the point 1 because the point 1 is between these 2 points, this point here and this point here. So this should maybe give us a vertex. So if we look at -1, if we look at 1, positive 1, we will get -1, 2. So our curve goes out a little bit. So actually, we've got some that looks like that, and that's symmetric. Okay, so now we can actually graph this. So it's gonna, and I'm sorry for my freehand, but looks something like this curve. And we're gonna have a little vertex there. We're gonna keep going out. We're gonna pass through this guy. And our curve is moving this way through time. Put some arrows there to indicate which way our graph is going, and that's really the graph of it. So it's a fairly straightforward idea, and there's another way to do this, which is a little bit more mathematically involved, and that's a tool that you might want to use, and that's called elimination of the parameter. So if you see in this set of equations, if you can solve for t in terms of y or t in terms of x, well, then you can substitute that into the equation for the other variable, and you can arrive at an equation that describes the curve either implicitly or explicitly, but you'll get a curve in terms of x and y, and sometimes that can be easier to graph, sometimes it won't be so easy to graph, but the idea here is, I think, is that the brute force way always seems to work, but elimination of the parameter also works. Anyways, why don't we look at the elimination of the parameter method. So we want to determine what the curve is defined by the following set. So we let x of t equals cosine of t, and y of t is equal to sine of t. Cost and cent. I don't really like that, but that's okay. Anyways, what we can do, and you're not always going to be solving for x and substituting in for y. Sometimes you need to recognize some trig identities or something like that. But anyways, in this case, we should recognize that if we square x and y, we're going to get something nice such that the cosines and the sines cancel out. So if we square x of t and then square y of t, get cosine square root of t plus sine square root of t. Of course, that's equal to 1 by the Pythagorean theorem for the trigonometric functions, sine and cosine. Of course, this is the unit circle. We get x squared plus y squared is equal to 1. So cosine squared of t plus sine squared of t is equal to this guy here, the unit circle, and we go that way because that's how the trigonometric functions travel along their circles. Anyways, thank you very much for watching this video, and in the next video we're going to discuss derivatives of these guys. So it's going to be kind of like, but not really like, implicit differentiation. We will look at that in the next video, though. We'll see you then. Bye.